You have probably heard the phrase that 2 points make a line and 3 points make a plane. What that means is that if we have 3 points that do not lie along the same line, then we can define a plane that goes through those 3 points. Another way to think about that is that we can take those 3 points and we can create 2 vectors. And those 2 vectors we can use to define the entire plane. But another way to think about that is once we have 2 vectors, we can construct a third vector, and that third vector is perpendicular to the first 2 vectors and is therefore perpendicular to the entire plane. So a natural way for us to define a plane is to take a single point and a vector that is going to be perpendicular to the entire plane. And if we have those 2 pieces, then we can define a plane, the set of all points that is perpendicular to that single vector, but also contains a specific point. So let's look at this in more detail. We'll have a definition. A vector which is perpendicular to every vector in the plane is going to be called a normal vector. And we will use that to define the equation of a plane. So let's look at the plane that I've drawn for you. I'm going to make sure that plane contains a specific point. We'll call that point R0. R0 is going to be the point x0, y0, z0. And then I'm going to define a normal vector which is perpendicular to the plane. That normal vector n, I'm going to call A, B, C. Now, one way to think about that normal vector is it's not just perpendicular to the plane, it's perpendicular to every vector that's contained in the plane. So in some sense, it's perpendicular to that vector, to that vector, to that vector. It's perpendicular to all of those vectors. So what I'm going to do is I'm going to define an arbitrary vector in the plane. That arbitrary vector is going to be the vector that runs from R0 to R. Now R, I'm going to label, because it's arbitrary, is the point x, y, z. And so we're going to define our plane by looking at all of the points that are going to be perpendicular to that normal vector. So we're going to think of our plane as being all of the vectors that go from R0 to R that are perpendicular to the normal vector n. So in other words, our equation is going to be that our normal vector is going to be perpendicular to all of the vectors r minus r0. Now, if the normal vector is perpendicular to all vectors r minus r0, then the dot product of our normal vector with r minus r0 must be 0. And so this is our equation of the plane. Sometimes we like to put the r0 on the other side, so we would write it as n dot r is equal to n dot r0. Now, let's see what this looks like if we expand it out with coordinates. So first, I'm going to take n dot r. So n dot r minus r0. What does that look like? Well, if I take n and I'm going to dot it with r minus r0, so let's remember that r minus r0 is going to be x minus x0, y minus y0, z minus z0. Then n dot r minus r0 is going to be a times x minus x0 plus b times y minus y0 plus c times z minus z0 is now going to equal 0. Another way we can write that is we can expand this out. That'll be ax plus by plus cz. And then that equals, well, we can put all the constants on the other side and we'll just call that d. And that's probably an equation of the plane that you are familiar with. Notice that it kind of looks like the equation of a line, except for that we've added a third dimension here. Okay, let's move on to some examples. The first thing that we're going to want to do is find a plane that contains the point 3, 2, negative 1 and has a normal vector of 1, 2, 3. So we want n dot r to equal n dotted with the point 3, 2, negative 1. So taking one more step, that's going to be n dot xyz has to equal n dot 3, 2, negative 1. So n in this case is 1, 2, 3. So let me put that in. And so we will get that x plus 2y plus 3z, taking the dot product of the left side, is going to equal 1 times 3 plus 2 times 2 plus 3 times negative 1. So our plane is actually x plus 2y plus 3z is equal to 3 plus 4 minus 3, or 4. Now I want to picture this in 3 dimensions. So I'm going to plot that plane. So I'm going to solve for z so I can plot that plane. And then I want you to see that the normal vector is 1, 2, 3. See, you can see that it's perpendicular to the plane, the point 1, 2, 3. And then I'm going to, the vector 1, 2, 3. And then I'm going to put the point 3, 2, 1, 3, 2, negative 1 in there so you can see that that point lies on the plane. Okay, now let's look at another example. We said before that 3 points make a plane. So let's see how that works. From those 3 points, we're going to create 2 vectors. Those 2 vectors are going to be the vectors PQ. The vector PQ is 3 minus 2, which is 1. Negative 1 minus 0 is negative 1. And 3 minus 2 is 1. And then I'm going to look at the vector PR. And that is going to give us 1 minus 2, which is negative 1, 2 minus 0, which is 2, and 0 minus 2, which is negative 2. Now, those two vectors are in the plane, and so now I want to find a third vector which is going to be perpendicular to the plane. So my normal vector is going to be the cross product of PQ and PR. So I'm going to fill in the vectors. And then the cross product is going to be, well, it's the matrix 1, negative 1, negative 1, 2. The determinant of that times I minus, excuse me, that's not quite right. It's actually the matrix negative 1, 1, 2, negative 2 times I minus the determinant of the matrix 1, 1, negative 1, negative 2 times J. And then finally, plus the determinant of 1, negative 1, negative 1, 2 times K. So let's work that out. So we have negative 1 times negative 2. So we're going to get 2 minus 2 times I minus, let's see, negative 2 minus negative 1 times J plus 2 minus 1 times K. And so our normal vector is going to be 0. Let's see. We're going to have a negative 2 plus 1 is a negative 1, but that's going to be then just a 1, and then a 1. So our normal vector is going to be 0, 1, 1. Great. Well, now we want to find the equation of the plane. So we're going to do our normal vector dot r. And then we're going to set that equal to our normal vector dot one of the points. I'll pick the point 2, 0, 2. So if we take our normal vector 0, 1, 1 and dot it with x, y, z, we're going to get y plus z. And then if we take our normal vector, or our vector, normal vector 0, 1, 1 and dot it with 2, 0, 2, we're going to get 2. And so in fact, the equation of our plane is going to be y plus z equals 2. And that should contain those 3 points. So let's look at this as a graph. So we have the 3 points. Those 3 points are 1, 2, 0, 3, 1, 3, 2, 0, negative 2. And we want those all to lie in the same plane. And so I'm going to plot y plus z equals 2, which is also z equals 2 minus y. And if we look at that plane, you can see that it indeed contains all 3 points. Let's move on to some further examples. I want to note that 2 planes are parallel if their normal vectors are parallel. Because the normal vectors are perpendicular to the planes, those 2 perpendicular vectors to the parallel planes must indeed be parallel. Now, if 2 planes are not parallel, then they intersect in a straight line, and the angle between those 2 planes is the acute angle between their normal vectors. So we either have that 2 planes are parallel, or those two planes intersect. But if they intersect, then we can actually define the angle of intersection for those two planes. So let's find the angle of intersection between the planes x plus y plus z equals 1 and x minus 2y plus 3z equals 1. So the first normal vector for that first plane is the coefficients of x, y, and z, which is 1, 1, 1. And then the second normal vector, the coefficients of x, y, z are 1, negative 2, and 3. And now we want to remember something that we learned about the dot products. Specifically, we learned that the dot product of two vectors, n1 and n2, is going to be the magnitude of n1 times the magnitude of n2 times the cosine of the angle between them. So if we want to find the angle between the two planes, we can find the angle that's actually between the two normal vectors, and that will give us the angle between the two planes. So here I'm going to solve for cosine of theta. So cosine of theta is going to be n1 dot n2 over the magnitude of n1 times the magnitude of n2. So if we want to dot n1 and n2, then we should get 1 times 1 plus 1 times negative 2 plus 1 times 3. And then we're going to divide that by the magnitude of the first vector, which is the square root of 1 squared plus 1 squared plus 1 squared, and the magnitude of the second vector, which is the square root of 1 squared plus negative 2 squared plus 3 squared. Okay, so the numerator is going to be 1 minus 2 plus 3. So that's actually going to be 2. And we're going to divide that by the square root of 3 times the square root of 14. So the cosine of the angle is 2 over the square root of 42. So if we want to find the angle in radians, that's going to be 1.257 radians. Or we can convert that to degrees, and that's going to be 72.02 degrees. So these two planes intersect at an angle of 72.02 degrees. Now, we want to find the line of intersection between these two planes. So in order to do that, we're going to set z equals 0 to find just a single point of intersection. This is a little strategy. We have to find somewhere that the two planes intersect, and we suspect that there's a point where z equals 0 where they intersect. So then I get two equations, x plus y is equal to 1, and x minus 2y is equal, again, to 1. And what I'm going to do is I'm actually going to take the first equation and then subtract the second one. And so then I get that y plus 2y is 3y is equal to 0. So indeed, we can say that the planes intersect where y equals 0. Now, if y equals 0, that tells us that x, plugging that into the first equation, must be 1. And so our point of intersection of the two planes is 1, 0, 0. And you can verify that by just looking at those two equations, and notice that if we plug in 0 for y and z in each of those two equations, we do get that 1 equals 1. Okay, now that we have a point of intersection, we need to find a vector that is perpendicular to both normal vectors. Okay, so what we need to do is we need to do n1 cross n2. Okay, so that means that we have to take the cross product of 1, 1, 1 and 1, negative 2, 3. Now, I've already done a cross product, so I want to spare you the details. Okay, that vector is going to be 5, negative 2, and negative 3. So now, if we found a perpendicular vector to both normal vectors, then that's going to be the direction of our line of intersection. So the equation for our line of intersection needs to be a point. That point is going to be 1, 0, 0. And then we need it to go in a direction. That direction needs to be perpendicular to both of those normal vectors. And so that direction is going to be 5, negative 2, negative 3, and we're going to multiply that by t. And that's going to be our equation for the line of intersection. Let's see that line of intersection on our graph. So what I'm going to do is I'm going to take our plane. This is the plane x minus 2y plus 3z is 1. And then our second plane was 1 minus x minus y equals z, or x plus y plus z equals 1. Okay, I want you to notice when you're looking at the intersection that they do appear to intersect in a line. Okay. Also, look at the acute angle between them, 72 degrees, right? A little less than a right angle. Seems to be reasonable. And then now I'm going to plot that line that we just found. And I want you to notice that the line there is exactly the line of intersection for our two planes. Okay, so essentially, the idea here is that in order to find the line of intersection of the two planes, then you need to find a line that is perpendicular to both normal vectors. And that's how we did that. Okay, so let's finish off with one more example. And that example is to find the distance from the origin to the plane 2x minus y plus 3z is equal to 1. So we want to know essentially how far away is a plane from a particular point. So what I'm going to do here is in order to draw this, I'm going to draw the plane as being flat. So I'm going to think about rotating my coordinate system so that the plane that I'm looking for, 2x minus y plus 3z equals 1, is flat. And then I'm going to stick the origin, that point that I'm looking at, out here. I'm going to call that point P. It's a point that's not on the plane. Well, when I'm talking about the distance of a point to the plane, I'm talking about the perpendicular distance. So I'm thinking about there being a line down here that is perpendicular to the plane. Well, that means that that line has to fall along the normal vector. Okay? And that perpendicular distance is going to be the shortest distance from the plane to that point. Now, I don't know exactly where that point of intersection is. But if I know another arbitrary point in the plane, I'm going to call that point, say, P0. Then I can draw the vector from P to P0. And then I can think about the distance of the perpendicular distance from P down to the plane is actually the projection of that blue vector in the direction of the normal vector. So I'm going to call this vector from P0 to P, I'm going to call it B. And the projection of B in the n direction is going to be the distance from the point P to the plane. Now, why is that? Remember that the projection of one vector onto the other is going to be the amount of B that's in the n direction. And that's actually the distance that I'm looking for. I want to know how much of B is in the n direction. So if I want to find distance, I want to know how much of B is in the n direction. That requires a projection. That's the component of B in the n direction. Well, we've seen this previously. That's going to be B dot n over the magnitude of n. And so the best way to find the distance from the point to the plane is to find the amount of this vector B in the n direction. So to finish this off, this example, what we're going to do is we're going to pick a point on the plane. So it can be any point that's on the plane. So just to make things easier, I'm going to let x and z both be 0. So that way I know y has to be -1. And that point is now on the plane. You can substitute that point into the equation and see it's on the plane. And then I need to find the vector. I need to find the vector B. B is the vector that goes from P0 to P. Okay, and remember that P is supposed to just be the origin in this case. So I'm going to take the origin and subtract P0, and so if I do that, I'm going to get the vector 0, 1, 0. Okay, well that tells me that the distance from the point to the plane is going to be B dot n, so 0, 1, 0, dotted with the normal vector 2, -1, 3, and then that's going to divide that by the magnitude of n, which is the square root of 2 squared plus 1 squared plus 3 squared. So that distance, in fact, is going to be, the dot product is a -1 over the square root of 14. So one thing that we did figure out here is that this distance obviously can't be negative, so we need to look at the absolute value. So I'm going to take the absolute value here. And so it's in fact 1 over the square root of 14. Now, you can use this concept to define a formula, and the book defines a formula for the distance. But I don't like to memorize formulas. I like to think about things in terms of projections. And so I think about what is the projection of this vector B in the n direction, and that gives us the distance from the point to the plane.